Welcome back to my series about probability theory. In this video, we will continue with combinatorics, which is the branch of mathematics which focuses on counting. The focus will be the binomial coefficient, which allows us to compute the possible number of permutations of objects. This comes in handy when computing probabilities of poker hands, which will be one of the examples that we cover during this video. But let's dive into a simpler example first to demonstrate what we are doing. Assume that you have a group of 3 people. How many possible different teams can you form from them? Different in this case means that the order does not matter, so a team of A and B is the same as a team of B and A. We can simply start by testing out all different combinations, so first we have A and B, then A and C. Now we get to B and A, but we already had that one. Then there is B and C. The teams with C and A and C and B have already been there, so we also do not need them. For the final result, we would get 3 different possible teams for the answer. The binomial coefficient allows us to compute exactly this. If we write down 3/2, which is also called from 3 choose 2, we get the same result of 3 possible teams. We also call these permutations of the 3 objects. We have seen that if we would simply enumerate all possible combinations, as we have done it in sampling without replacement, where the order still mattered, we would get too many possibilities. This is also called overcounting. Let's compare the binomial coefficient case to the one of sampling without replacement. There, we had n factorial divided by n minus k factorial, which in this case would get us exactly the 6 possible combinations of people. But what exactly is this binomial coefficient? What do we actually compute and mean when we write down n over k? The full computation rule for from n choose k is the following fraction. In the numerator, we have the sampling without replacement rule. However, this would lead to overcounting, which is why we still need to correct for overcounting based on the number of samples that we obtain. As always, we are not allowed to take more samples than we have objects, so k needs to be less or equal than n. We can illustrate why we need the correction for overcounting with an example. Let's assume that we have 4 objects, so n is equal to 3, and want to take 3 samples, which means that k is equal to 3. The final order of the 3 samples does not matter. We will choose one of the 4 objects and put it into a box with 3 spots. For the first sample, we have 4 objects to choose from and 3 spots to be chosen. If we only considered the 4 possibilities for the objects, we would overcount by a factor of 3, so we still need to divide by 3. In this way, the order of the outcome does not matter. Then, for the next sample, we only have 3 objects to choose from and 2 spots left in the outcome box. Thus, we simply multiply with 3 using the multiplication rule and divide by 2 to account for the overcounting. For the final object, we can choose from 2 and have 1 spot left, so we multiply with 2 and divide by 1. This exactly corresponds to the binomial coefficient. If we write out the formula for from 4 choose 3, this gives us the following. And finally, we have 4 different scenarios in which we can put 4 objects into 3 boxes where the order does not matter. We will take a look at 2 different examples where we can apply the binomial coefficient. Make sure that you also try to solve them on your own before you compare the results to the solution. In the first example, we want to compute the possible permutations of the letter in the words statistics. With permutation, I mean change of letters in the word, for example this one here. Consider that there are duplicate letters, which makes the problem a bit trickier. Let's get to the solution. We draw 10 boxes for the letters to go into, since the word statistics consists of 10 letters. We start with the letter S, which is present in the original word 3 times. Now we have 10 possible boxes in which these 3 letters can go into, so we compute it using 10 over 3. If we continue with the next letter T, which also is in the word 3 times, we only have 7 boxes left to choose from, since 3 are already occupied by the S's. The same procedure can be done for the letter A, always removing the already filled boxes and considering how many letters are present in the original word. We will also repeat it for I and finally for C. By utilizing the multiplication rule, we can simply multiply all the different combinations and get our final result. It is possible to arrive at the same result using the sampling without replacement method to compute all combinations of the letters and then adjust for overcounting by dividing by 3 factorial twice and once 2 factorial. This accounts for the fact that the letters are not only present once, but more than that. In the second example, we will compute the probability of a full house hand in poker. A full house satisfies the following conditions. You need 3 cards of one rank, which are for example 3 cards with the number of 10 on them. Then, you also need 2 cards with another rank, so for example 2 sevens. Remember that there are 52 cards in a poker deck, and we consider a fair deck, so all of them have equal probability of being drawn. As a first step, we write down the definition of the naive probability. In the denominator, we need the number of possible different hands. This can be done using what we have learned today, using the binomial coefficient. You can imagine it as drawing 5 samples from a deck of 52 cards, where the order does not matter. Then, imagine the tree of possibilities. In the first branch, you draw the first rank, which there are 13 of. You need to exactly draw 3 from the 4 possible ones. Using the multiplication rule, this gives us 13 times 4 over 3. For the branch of the tree afterwards, there are only 12 ranks left, since the first one has already been determined. There, we need to draw 2 out of 4, so we use the binomial coefficient with 4 over 2. In total, this gives us a probability of 0.0014, which is obviously very low. However, this is not even the poker hand with the lowest probability, since there is for example the royal flush, which is 100 times less likely. What this example shows is that first of all, when playing poker, you have very low odds of drawing good hands. Secondly, the notation of the binomial coefficient is very self-explanatory. In this example, we had from 52 choose 5, which, even out of context, is very clearly readable and linked to a hand drawn from a deck of cards. I hoped you learned something new from this video. If you are interested, check out my full playlist about probability theory, where I go over the fundamentals first, and step by step build up more complex topics that can be used also in practice.